Hello and welcome to my channel Physics for Students. My name is Shaunak and welcome to this video of Maxwell's equations. Well, in this particular video what we are going to do is that we are going to look forward into Gauss's law for magnetic fields in its integral form. We are also going to find out what is the origin of the term B. Why do we use B for magnetic fields and not C, D or any other thing? We will also discover what are the conventions that we use in Maxwell's equations and a fascinating history of those terms. Finally, we will also look into the implication of those equations of Gauss's law. What if we have a magnetic monopole? It's a kind request to all the viewers to watch this video till the end. It would be simple, straightforward, without too much of mathematical equations. We will deal with the integral part and then we will find each and every part of that equation and a great fascinating journey into the origin and roots of Maxwell's terms that he used in the equations. So watch till the end of the video. Please don't miss on any of these parts. Before we go ahead on understanding the equations, the first and the fundamental concept is that what is a divergence? This is a very important concept that we need to understand. Now, the word divergence actually comes from the word which means spread. It is coming from two Latin words, dis plus vergere. So it had its origin around 1650 and it is the modern Latin divergentia from divergence, which means going into different directions or from assimilated, verge to bend, turn and different things. So here is a kind of a picture which shows the divergence. So Maxwell actually coined the term convergence, mind it, not divergence, and it was not until this gentleman who coined the term divergence. I hope you can recognize him, Oliverheaviside. Yes, a person who popularized Maxwell's equations and coined the term divergence. So we get a positive divergence, we get a negative, and we get a zero divergence. So let us look into a little bit details on those. What do we mean by positive, negative and zero divergence? Okay, so first what we see is that what is called a positive divergence. Now, when we get this kind of a figure, you see these radially outward vectors where I have given the divergence by the opposite, reverse sign of delta, which is called the Greek nabla sign, which is greater than 0. So if you get a kind of a point like this, which is marked in red, and if we marked it as x0 and y0, then what happens is that, yes, you see all these blue lines which are diverging out. That means it is a kind of a spreading out. So you can just imagine it's a kind of a, so nabla dot v is greater than 0. So you can just imagine a point or a sink where the water is falling and the water is diverging out. That means it has got a positive divergence. So at some point x0 and y0, when it comes out to be positive, this is called a positive divergence. So the fluid flow, this is just an analogy, taking fluid as an example, along the vector field becomes less dense around. Why less dense? Because it spreads out. Now if you're really keen in understanding why we are using fluid, you will see in Maxwell's original paper, which is published by the Royal Society in England, he used the analogy of fluid. So it is not that we are just taking abruptly fluid and making it understand through divergence, but actually it is James Clerk Maxwell who took the analogy of fluid and made the equations possible further. So here is this region where the fluid is flowing out, so it becoming less dense, and hence it's called the positive divergence. So we get into negative divergence where it is less than 0. You can see that the radially pointing vectors are pointing towards a point. So we take a similar kind of an example with this red dot, which means a point, and here it comes. All the blue lines are pointing towards. So you can see that if there is a sink and the water from the tap is flowing, it is moving towards the base of the sink. So that is called negative divergence. So we take a similar example, x0, y0, and this one would be at some point of x0, y0, that the divergence is less than 0. And here it comes that the fluid flow along the vector field becomes more dense. Why more dense? Because obviously the fluid is pointing towards the point red dot. So open the tap and watch it on the sink. You will see that the flow of the water is flowing towards a certain point, and that is called what is called a negative divergence. Again, to remind the viewers that the analogy of vector field and the fluid is basically originated by Maxwell's original concept. So finally we come towards what is called a zero divergence. So here you see that the lines are going up as well as going in and out, in and out. So we got the del dot V, which is 0, and here is the same analogy, and you can see here. So these are coming in and coming out, coming in and coming out. So ultimately it leads to 0. So at some point x0, y0, the fluid flows freely. That means the fluid is coming in, the fluid is flowing out, but the density remains constant. Obviously, because when the fluid is coming in, find out for incompressible fluids. So this is how the zero divergence is taken an analogy, that the water is flowing in and then it is going out. So these are more or less the concepts of a positive, negative and zero divergence. This is an important concept in Maxwell's equations. So it is that when it comes out 0. So just kind of a quick brush up on what is actually divergence. Okay, so what is the meaning of the integral form of Gauss's law? So what we see is this one. We will, don't worry, we will understand these concepts in a few minutes more. So here are a few of the analogies. So meaning, so in other words, what we can see that if we have a real or imaginary closed surface of any size or shape, the total magnetic flux through that surface must be 0, right? I again repeat, if we have a real or imaginary closed surface of any size or shape, the total magnetic flux through that surface must be 0. Just a kind note that this does not mean that 0 magnetic field lines penetrates the surface. It means that for every magnetic field that enters the volume enclosed by the surface, there must be a magnetic field also leaving that volume, right? So that is the inward negative magnetic flux must be exactly balancing by the outward positive magnetic flux. These are few of the points. The magnetic field has 0 divergence. The total magnetic flux passing through the closed surface is 0. For every magnetic field line that enters the closed surface, there must be a line which is going out of the surface. This is the overall meaning of the left hand side part of the equation. Okay, so first of all, let us understand what is the key difference. Now, when I say key difference, what I'm trying to tell you is that this kind of a figure where you get an positron and electron, let us not consider the neutrino right at this moment. The key difference in the electric field and the magnetic field, I mean to say, when we have learned, if you go to my playlist, you will understand that I have earlier shown Gauss's law on electric field. So the key difference in the electric field and magnetic field versions of Gauss's law arises because opposite electric charges, I mean to say positive and negative, may be isolated from one another, while opposite magnetic poles, which is north and the south pole, always occur in pairs. Let us see this part, which is marked in red, black. So this is the negative one and this is the positive one. These can be, charge, yes, can be isolated, which is called monopoles. Whereas this kind of a figure on the right hand side of the screen, this is a kind of a magnet, bar magnet, and this north and the south pole, which you see is marked in yellow, cannot be isolated. This is the key difference, that it can be isolated. Example, positron and electron, here it cannot be isolated. So as you might expect, the apparent lack of isolated magnetic poles in nature has a great impact on the behavior of magnetic flux and overall on the divergence of the magnetic field. So this is a kind of a quick note that you might find that what is the key difference between electric and magnetic, right? So first of all, then we go forward and we now understand what is called the integral form of Gauss's law. Now note to the viewers that you will soon find that both the integral and the differential form is not dealt in this video, has more or less the same impact. Okay, so this is the equation in integral. So let us find out what it is. This part on the left hand side of the equation, right, the left hand side of the equation is a mathematical description of the flux of a vector field through a closed surface, right? This is the flux of a vector field through the closed surface, and this one is actually identically 0. So in this case, Gauss's law referred to magnetic flux, the number of, you can imagine just as the number of magnetic field lines passing through a closed surface S, the right side is identically 0. So here is another figure. Let me show you another once more. So these lines, yeah. So this is a kind of a imaginary Gaussian surface. The number of lines entering the Gaussian surface is equal to the lines leaving the surface. Now, isn't it beautiful that the books should balance, right? I mean to say in nature or in physics and mathematical models also, what we get is that, we can talk it in a computer language as garbage in and garbage out, but philosophically also, if you take it, then this is where the nature balances its own book, and what comes in equally goes out. In this case, the case of the magnetic field. Okay. So let us dissect this equation. I mean to say, let us see that what actually this equation is all about. Right. So we get this equation, and this one, the integral part, is the total sum each point of the surface. Okay, so S is basically the surface integral, not a volume or line integral. This one, the arrow on the top actually denotes that it is a vector quantity. So B is the magnetic field, which is measured in Teslas, and we are going to soon discover that why it is we are taking B. Okay, so this one is the dot product, which we have already dealt earlier also. Dot product to find that part of B which is parallel to N. Oh, the hat over the N is actually the unit vector normal to the surface, which means that it is 1, right? It is a unit vector. A is the increment in the surface area of M square, and D is what we are differentiating. So this is overall, once we dissect this situation, we get this kind of an equation. And now that we have understood each and every part, so we really understand what this equation is all about. So these are the components, these are the parts, sorry. So you can easily understand that what this equation is all about. Yeah, so it tells that magnetic flux across any closed surface is 0. So for example, if I can say that we have a collection of charges, then electric flux lines start on a positive charge and end on a negative charge, and they get closer and closer and closer together the closer we get to the charge. So positive charges are said to be the sources of the electric field, and negative charges, you can call it as a sink, right? But there are no magnetic charges, so magnetic flux lines have nowhere to begin or end. They form closed loops. Okay, so this is how we formalize the concept in a slightly different way. So we move on to the next part of our video, where we find that what is a magnetic field? I mean to say, what actually this magnetic field is all about. So this one, this B, this is called the magnetic field, right? And E is the electric field, right? We know that. Now, let us begin that there are two types of forces. Okay, so this is the bar magnet, just to give you a visualization. So a magnetic field is a vector field that describes the magnetic influence on moving electric charges and I would say magnetic materials, right? So this is how it all happens. Now, yeah, so let us begin with two types of forces. Contact forces we know, and when you have non-contact forces. This is just to give you an intuitive understanding. So as the name suggests, contact forces are existent when there's a some kind of a contact between the bodies exerting force and experiencing. Now forces like magnetic forces, for example, comes under non-contact forces. So how do these forces act? How can some object experience a kind of a force without a contact? So answer this question, the concept of field actually is brought upon, which is right there on the screen. So field was basically a kind of a region around an object exerting non-contact force. In this case, for example, a magnet. So where there are objects having similar properties experience a force. So a magnetic field, having similar properties was deliberately written to, I'm stating so that these non-contact forces can act not on all bodies, but on bodies which have certain specified property For example, if you want to be an object to be affected by magnetic field, then it must have a magnetic property. So here on your screen, a magnetic field is generated when electric charge carriers such as electrons move through a space within an electric conductor, right? And Gauss's law states that magnetic monopoles does not exist. So if you have a collection of, a kind of a charge, then electric flux starts on a positive charge and ends on a negative charge. But in case of, I would say, magnet, it is not forward. So this entire integral part, and once we develop further, we will see that it actually shows that magnetic poles does not exist. So this is a kind of an intuitive and a clear understanding what do we mean by magnetic fields. So there are no sources or sinks for the magnetic fields. Obviously, if there are sources on sinks, then it will diverge in some other direction. So it has got no sources. It cannot go into somewhere. So it will constantly go into a kind of a loop. So there are no sources and there are no sinks, right? Okay, so now what we come forward is that now in physics, in electromagnetism, there is something which is called a Lorentz force. Now, electric force and magnetic force, so the electric force and the magnetic force, both of them combine on something which is called a Lorentz force. Now, the Lorentz force or electromagnetic force is the combination of electric and magnetic force on a point charge due to electromagnetic fields. Now, a particle of charge q moving with a velocity v and on an electric field E with a magnetic field B experience a force which is given by this, right? So let us see what it is. This one is basically the q is the charge, E obviously is the electric field, V is the velocity, and V is the magnetic field, right? So it says, so what does this equation suggest? So it says that the electromagnetic force on a charge q is a combination of a force in the direction of the electric field E, which is proportional to the magnitude of the field and the quantity of a charge, and a force at right angles to the magnetic field B and the velocity v of the charge is proportional to the magnitude of the field, the charge, and the velocity, right? So variations on the formula describe the magnetic force on a current carrying wire, sometimes called Laplacian force, the electromotive force in a wire loop, and so on. Now, what I'm trying to tell you is that you saw that I told a lot into English, but this is something which we can write. So just as the electric field may be defined by considering the electric force on a small test charge, the magnetic field also may be defined using the magnetic force experienced by a moving charged vehicle. So here is a kind of a graph. So the red one, the velocity moving in this direction, we got a force, and we got a kind of a almost 45 degrees angle, which is this B, right, and a point charge Q, right? So what we get is this. So just as the electric field may be defined by considering the electric force on a small test charge, the magnetic field may also be defined using the magnetic force experienced by a moving charged particles. Okay, so so as you may recall that charged particles experience magnetic forces if they are in motion with respect to the magnetic field, as shown by Lorentz equation, this one, right? So EMF, electromagnetic force on charge Q, combination of force, electric field E, force is at right angles, magnetic field is at V, and velocity is at V. So now what we can do is that we can write in this way. So here what happens is that this is the Lorentz equation for magnetic force. Okay, let me show it once more to you. This is the Lorentz. So FB is the magnetic force, Q is the particle's charge, V is the particle's velocity, with respect to B is the magnetic field. So what exactly we have done is that we have just taken away the charge in the electric field and we got what is called the Lorentz equation for magnetic force. You might be wondering why we require the Lorentz equation. This is important in terms that we take the normal Lorentz force method, and then we just substitute this sub B, F sub B, which means for force by magnet, and then we eliminate the QE part, and what we get is the Lorentz equation of force. So again, I would like to tell you that just as the electric field may be defined by considering the electric force on a small charge, similarly, the magnetic field is defined using the magnetic force experienced by a moving charged particle, which is this blue one, that B. So electromagnetic force on charge Q, combination of force electric field E, force is at right angles, magnetic field V, and velocity V. Right. Okay. So here is something which is quite similar to you. We use this definition of the vector cross product, which says that if this one A and B is there, so right, A multiplied by B gives AB sine theta, where theta is the angle between A and B, and the magnitude of the magnetic field can be given as this, right? So you see the sine theta angle, which is marked in blue, right? So the terminology for magnetic quantities, now this is from AB sine theta, that what we do is that we take a vector cross product, and then using theta as the angle between A and B, we calculate the magnitude of the magnetic field, which is this B, right? Remember, B is a vector, so we put an arrow on the top. Now, one thing is important. The terminology for magnetic fields, that is B, is not as standardized as the electric quantities. So what is happening is that we are likely to find text that refers to B as magnetic induction. Sometimes it is called magnetic flux density, whatever. I mean to say the different terms. So whatever it is called, this B has units. For example, N/am is Newton per ampere meter. This is volts per second meter square. Then we have got Tesla and so on. So these are, kinds of measurement. And this 1 Tesla equal to V multiplied by C by M square is similar to Newton per ampere is equal to G, and so on, right? So this is a kind of a understanding that what is a magnetic fields. Because it is not standardized, we get sometimes called magnetic induction, sometimes we call it at magnetic flux density, whatever we call it. This has been measured, and these are the units. Okay, there are some observations which I would like to tell, which is very important for all of us to understand, is that if you take magnetic field, for example, I won't say magnetic field, it would be the magnitude of the magnetic field. And if you take the electric field, which if you go to my playlist, you will understand it's there, and draw a line, then there are certain things which are very important to observe. One is that the magnetic field is directly proportional to the magnetic force, where electric field is parallel or anti-parallel to the electric force. In magnetic field, force is defined through a small test charge. So we take a small kind of a charge and move things around, but the speed of the direction of the test charge must also be taken into consideration. In electric field, force is defined through a small test charge. Now, work done by magnetic field here is 0. Work done by electrostatic field on a charge moving around a closed circular or an elliptical path will be 0. And magnetostatic fields are produced by electric currents. Electrostatic fields are produced by electric charges. Very important. Few great observations, I would say, just taking magnetic field and electric field. You can just go through it, take a snapshot. It's important for students to understand what would be the intricacies between, I won't say difference, but a relation between magnetic and electric field. Okay, so magnetic field sources. Let us see what are the magnetic. These are few of the photographs and pictures. So magnetic fields may be represented using field lines, right? These are the field lines you can see whose density in a plane perpendicular to the line is proportional to the strength of the field. So these are the figures. But there are certain, again, few good observations which is worth noting. First is that magnetic field lines do not originate or terminate on charges, right? They are always creating loops, and that is why they don't have a sink. So you see, you can understand all these, the bar magnet, the electromagnet, the disk magnet, the bar magnet, the earth, all of them are creating loops. This is very important to note. The second one is that the magnetic field lines that appear to originate on the north pole and terminate on the south pole of a magnet actually makes a kind of a loop, right? Okay. The net magnetic field at any point is the vector sum of all magnetic fields at that point. So if you want to calculate the magnetic field at any single point, any point on a kind of an object, it is a sum of all magnetic fields that are present. Okay, and finally, magnetic field lines never crosses. It never happens. So this would indicate that the field points in two different directions at the same location. If the fields, form two or more sources overlapping at the same location, they would add to produce a single, which is the total field at that point is not right. So that's it. So this is a kind of magnetic field sources, and why do we need to understand the magnetic field? Okay, so we now move on to the most important and very interesting part, that is, why do we use B for measuring magnetic field? We are going back almost way back, and we are going to see the roots, and we are going to understand, right? On the left hand side of your screen, what you see is a book, right? It is a dynamical theory of the electromagnetic field. Now, what I would like to tell you is that this book, if I talk, is a paper of James Clerk Maxwell on electromagnetism, published in 1865, right? And in the paper, Maxwell actually derives an electromagnetic wave equation with a velocity for light in close agreement with the measurements made by the experiment, and deduces that light is an electromagnetic wave. Now, following standard procedure for the time, the paper, so here is the great person, James Maxwell. Now, following the procedure of that time, the paper was first read to the Royal Society on 8th of December 1864, and it was sent by Maxwell on the Society on 27th of October, and it went obviously for a peer review. And during that time, William Thomson, who was later known to be Lord Kelvin, reviewed that on 24th of December prior to the Christmas in 1864, and it was further sent for processing. Now, it was approved around 15th of June in 1865, right? It was approved around 15th of June 1865 and was sent to the printer. And during this period, the Philosophical Transactions was only published as a bound volume once in a year, and it would have been prepared by the Society's anniversary day on day 30 November. However, the printer was not been prepared and delivered to Maxwell's offprint. So this is a kind of a small overview on the work which Maxwell did on this phenomenal book, A Dynamical Theory, and how it was presented and went through a peer review by Lord Kelvin and finally got published. Right. Now, what happened is that the original Maxwell's equations were not 4 or not 8, it were 20 equations. Now, in part 3 of the paper, if you read the original paper, you will see in the part 3, there's a title called General Equations of Electromagnetic Field. And Maxwell formulated 20 equations, which came to be known later as Maxwell's equation, until this term, become applied instead of vector set of 4 equations. So here are those 20 equations right on your screen. So the 3 equations of magnetic force, you can see he is using H. The 3 equations of electric currents, this is more or less of a kind of a current density, you can tell. And these are the 3 equations of electromotive force. Okay, we go further, right? And what we find is that 3 equations of electric elasticity, equations of electric resistance, 3 equations of total currents. Okay. And then we further find 1 equation of free electricity and 1 equation of continuity. So total, I would say it makes up 20. Right. Okay. So now these 20 equations were later reduced to 8 of those equations. Right. So why I'm telling this, because then you will understand the concept of using B. Now, when it is reduced to this obviously research I have not done, but I have taken from Philosophical Transaction. This is by Malcolm Longear, and I have given the entire screenshot so that if you really want to read, you can go to royalsocietypublishing.org and you can go ahead with that. So this shows on history that how these 20 equations got reduced to 8 equations. These are the reduced 8 equations. Okay. Now, what happened that in 1873, Maxwell published a treatise on electricity and magnetism. Now, here I would like to say that Maxwell actually published more than about 100 scientific papers, while his main claim to the fame lies in his work on electromagnetism and the theory of kinetic theory of gases, which we are not considering. Now, he actually concluded not only that light and magnetism are affections of the same substance, but also that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws, right? Treatise on Electricity and Magnetism, which is on the left-hand side of your screen, is a 2-volume treatise on electromagnetism written by James Maxwell in 1873. Okay, Maxwell's was revising the treatise for a second edition when he died in 1879, and a third edition was prepared by J.J. Thomson for publication. It went to 1892, right? So here, right on your screen, these equations got transformed into electromagnetism, and here you can see that A is used as vector potential, B as magnetic induction. Now I'm going to show you the original paper so that you really feel great and excited. It took me long, almost about a day, about 498 pages of Maxwell's original book, and find out the Greek letter where he used it. Left hand side of the screen shows you the treatise on electricity and magnetism, the original book, and the publisher's name, volume 2. This is actually where he deduces page number 236. Now, if I further zoom it, you will find this. So right on your screen is the origin, and this is the answer. Why do we use B? And not only B, let us see forward. So here, this one, rounded one, is the magnetic induction, right? This is denoted by B, and that is why we use B for magnetic field, which has been further revised by Oliverheaviside. This is also the next page, 237. So here it is, and if I further zoom it, you see the magnetic force, which we nowadays noted by H, is also here. Further we go forward in the book and we find the constituents of the principal vectors. You see this one, the magnetic induction and the electric displacement. So we know B as the magnetic induction and we know D as the magnetic electric displacement. This is the formula, and it exactly matches with the manuscript of James Maxwell. So right on your screen is the original manuscript, and below is the formula, so that you really now understand the roots, why B is used for magnetic induction, why D is used for electric displacement. Now this is another page where I can zoom further and we can find out electromotive forces marked in red and magnetic force, which is H. So we can calculate this one as electromotive force, which is E. I'm so sorry, that is E. EFGH, right? And then we calculate the magnetic field strength, which is denoted in a curly H, which for some purpose and with the scientific involvement has resulted into this. So you saw that from the 20 equations, which was originally there in Royal Society, it was reduced to 8. And the reason we use B and E and H for magnetic field, electromotive force and magnetic induction, you can further go back if you really want, and you can say this. This is the reason of using magnetic induction, the formula as in B. So these are the two. So electromotive force, which is used, FGH as magnetic field strength. Now when physicists today write down Maxwell's equations in their standard vector form, or simply set up a problem using vector analysis, they are drawing, usually without realizing, it is the work of this gentleman, Oliverheaviside. When we analyze how electromagnetic waves move along a wire or across a space, and we use words like impedance or inductance, we are again following Heaviside's footsteps. Now, Heaviside did much to develop and advocate vector methods and vector calculus. Maxwell's formulation of electromagnetism, originally, as you saw, consisting of 20 equations into 20 variables, Heaviside introduced the concept of curl and divergence operators in the vector calculus to reformulate 12 of these 20 equations into 4 equations into 4 variables. Let us see them. This one denotes the electric flux. This one is the magnetic field, which does not diverge. This is a differential form, which we can explore in the next video. I've already shown you the the integral form. And this is a summary of Faraday's electromagnetic induction and the magnetic in a closed loop equal to the current through the loop, right? So these are the equations which I would say that which is a lesser known person, Oliver Heaviside. I call, he is basically a self-taught mathematician, modernized, formalized those 20 equations, but he kept the original manuscript, the B and E, as proposed by Maxwell. These are the reduced 4 equations. So that gives you kind of an overview, and you now understand that why B is being used, what is the original paper like. We come to the last part of the video, which talks of Gauss's law and its effect on magnetic pole, or rather I would say magnetic monopole and its effect on Gauss's law. Now, a magnetic monopole, as you understand, is basically a hypothetical elementary particle, right? It is not yet discovered, and I would like to draw the attention of the viewers that whatever I would be telling now, these are hypotheses. Nothing has been discovered as of now. So what I'm all trying to do is that I'm trying to get a kind of an hold or a kind of a guess, I would say an intelligent guess, what would happen if we discover a magnetic monopole and what would be its effect on Gauss's law. So here on the left-hand side of the screen is the integral form of Gauss's law of magnetic field. This is the differential form, and more or less both of them suggest that there are no magnetic monopoles. So we told that magnetic monopole is a hypothetical particle, that is an isolated magnet with only one, either a north pole or a south pole. Now, a magnetic monopole have a net north or a south pole, south magnetic charge. Why? We just noted that whatever it does, we get the net one. So modern interest in the concept is still going on. It stems from particle theories, notably the grand unified and superstring theories, which we are discovering, or maybe we will discover. Right. So what I would like to show you is the first hypothesis. Again, kind note to the viewers, this is wrong, I know, but it could be anything. But let us try to get a kind of a wise guess. What if we find the magnetic monopoles? So a magnetic monopole needs to be something which is similar to electric monopole, right? Now, a stationary electric monopole does not produces any magnetic field. So a magnetic monopole obviously can produce no electric field. So I can deduce that the Gauss's law, stationary electric pole produces no electric field. So I can say that the Gauss's law remains the same. Now, and also the Gauss's law takes the form of this. Now, I would say this is the magnetic permeability of free space, and this is the volume density. So this is more or less, again, my first hypothesis, which I'm trying to show you. Okay. Now, we continue with the first hypothesis. Now, what I would like to tell you is that we also know that the electric current produces a magnetic field, right? So it also must be that a magnetic current produces an electric field in a similar fashion. So that is, we have to add a kind of a term proportional to the magnetic field, magnetic current in the Maxwell-Faraday law. Now, if you do a kind of a dimensional analysis, right, the proportionality constant should be either plus or minus, okay, but we do not know what. So what we can do, we can address the Lenz's law, and we know that an increasing magnetic field induces an electric field that drives the current through a loop according to the left-hand rule, right? So that the current produces an opposite magnetic field by the right-hand rule. Now, suppose that an increasing electric field must induce an opposing electric field in wire, right? So this is already, I have spoken right-hand rule, etc. So what we get is that because the changing electric field induces a magnetic field according to the right-hand rule, the magnetic current obviously produces an electric field according to the left-hand rule. So here is the Faraday's law, the original Faraday's law, which I can say is being changed to this. And what is this? This is the electric current density. So all the differential part of magnet and time remains the same. And we have just added what is called the electric current density. And obviously the Ampere's law remains unchanged, right? Again, this is a kind of a hypothesis. If we find a magnetic monopole and we work on Gauss's law, what would be the effect? Now, what we can do finally is that we can work out on the modified Lorentz law too, right? We can modify it, and obviously a magnetic field drives a positive magnetic change in the same direction. So what I can say, we know an electric field also has an effect of moving magnetic charge. So two electric currents attract Since electric currents attract when they are in the same direction, the same must be true for the magnetic currents, obviously. Since a magnetic current produces an electric field given by a left-hand rule, an electric field must also act by a left-hand rule on moving electric charges. So further doing a kind of a dimension analysis considering the speed of light, we get something like 1 upon c square, and this Lorentz law, which is now right on your screen, gets modified into this, right? Okay, so yeah, so this is a kind of first my hypothesis that what would happen doing the dimension analysis. Further, we can what we did in the earlier slide, if you go, what we did is that there was a modified form of Maxwell-Faraday's law, but the Ampere's law remained changed. Here, the Lorentz law using the dimension analysis changes. Okay. Now, in 1931, this gentleman, you all know, Paul Adrien Maurice Dirac, proposed the existence of a single magnetic monopole in the universe and would suffice to explain what is called the quantization of electric field. Now, in 1975 and 2019, intriguing results suggested the possible detection of magnetic monopoles, but unfortunately till date there is no direct evidence. Now, the quantum theory of magnetic charge started with the paper of physicist Paul Dirac in 1931. Okay, so P.M. Dirac in 1931 quantized singularities in the electric field. So in this paper, Dirac showed that if any magnetic monopoles exist in the universe, this is the paper marked in red border, then all electric charge in the universe must be quantized, as this is called Dirac quantization condition. Now, the electric charge is in fact quantized, which is consistent with but does not prove the existence of monopoles, right? So here is an extract of the paper which he writes, our theory thus allows isolated magnetic poles, but the strength of poles must be quantized, the quantum mu sub 0 being connected with the electronic charge E by so and so. This the equation. Right. So what I'm trying to tell you is that apart from all those, things that we learned, this is one of the most profound development in terms of magnetic monopole, but it has not yet been proved. So this is the second, I would say the first leap for mankind to discover, quantize and find out magnetic monopole. We go into the second, it would be actually the third hypothesis, but anyway, we consider the second hypothesis. Now, this is by some gentleman, I will just show you. Now, what he does is that monopole is a consequence of the existence of duality symmetry. And although no conclusive experimental evidence has been found in the definition of classical magnetic monopole, which we saw just by Dirac. Now, yeah, this is actually by Greg Houle. And he published this in Journal of High Energy Physics, Gravitation and Cosmology way back in 2018. And let us see what he proves. So in this particular part, what we see is this one. The abstract tells the most important that this paper confirms the theoretical existence of the magnetic monopole and calculates its magnetic charge using the ratio of the electromagnetic field and speed of the light. I have given the description, the original paper in the description box of this video. If you want, you can go. So this is actually the abstract which claims to prove this. Now this is the next kind of a calculation what he does. And here you can see he uses the Gauss's law and Gauss's, electric and magnetic law. And you obtain this, the ratio of the electric to magnetic fields in electromagnetic wave. So this is something quite interesting. He goes further forward and what he does is that, yes, this is one. He calculates the monopole mass and he further reduces to unit in kilogram second meter and the conversion of the factor into what is called giga electron volt. So this is a kind of a, he tries to deduce from this. This is the next one where he uses this one. Very important. Radius of the magnetic monopole at 2.8 into 10 to the power, 10 to the power minus 15 meters. So he writes, this calculation confirms the assumption of Giacomelli and Patzidis regarding the properties of magnetic monopoles, where their paper states the radius of the monopole and the electron are the same. It is quite, so the radius of the monopole and the electron are the same. So R sub n is the radius of the monopole. As you see, R sub E on the top is the radius of the electron. He further goes forward and calculates the wavelength, which is this, and it equates to the Planck hypothesis, which is equal to h nu. And here he states that we obtain a quantum energy of magnetic monopole to be this one, which equates to 0.22 giga electron volt. So I'm just showing you that as per the paper which has been published over the internet in this journal, what this researcher is claiming to. Finally, we come to the conclusion. This is the conclusion part. A very important few notes. So a magnetic monopole is a hypothetical elementary particle physics that is isolated. This is this. And then he writes that when Maxwell's equations are rewritten with magnetic charge included, the existence of monopoles is consistent with the updated equation. And then he further writes here that the two reciprocal proofs confirm the validity of the law of universal magnetism and also provide proof of the existence of the magnetic monopole. The law of universal magnetism and monopoles are mutually dependent. So, I mean to say, this actually concludes our video. So, I mean to say, I took a little bit time to research, go through the papers and understand what it is. So here is the summary, what we have learned. We have learned what is the divergence. We have also learned the meaning of the integral form of Gauss's law. We have dissected those equations more or less in a pretty easy manner, and we have understood what it is. We have also seen what is a magnetic field, the lines, the implications. We have gone past to Maxwell's original manuscript, I want to say original paper, and why do we use B? And we have also seen the Gauss's law and its implication of further researches in magnetic monopole. That's all for this particular video. Please do let me know in the comment box what is your opinion about this video. Do like, subscribe, comment, and click on the bell icon and click on all to get all the notifications from Physics for Students. I will be coming up in the next video. What we will do is that I'm going to show you the differential form of Gauss's law for magnetic fields and few of the important features. I hope you liked this video. I try to make it simple, clear, to the point, and something very interesting which you would enjoy. So this is Shaunak signing off from Physics for Students. Hope you have a great day ahead. Stay safe, stay happy, and wish you a very happy learning. And I will wait for your comments. Bye and have a good day ahead.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.